Hello everyone, my name is Lauren and welcome to Physics 2212 Experiment 1 Charged Tapes Report. The purpose of this experiment is to prepare charged pieces of clear tape in order to determine the amount of excess charge found on one piece of clear tape. Some fundamental principles necessary for this lab are Coulomb's law, which gives us the electric force of an object and from which we can determine the magnitude of the electric force on said object. The gravitational force, which we assume is near the Earth's surface, and Newton's second law, which states that the net force on an object is equal to change in momentum over change in time. We will assume that air resistance is ignored, that both tapes have the same amount of charge and the same charge distributions, and the tape acts as a single point charge. The last two assumptions will be applied separately in our two computational models. The main results of this experiment are an experimentally calculated electric charge of 1.166 times 10 to the negative 8 coulombs, a very similar computational point charge, and a very different computational line charge of 1.96 times 10 to the negative 3rd coulombs. The initial conditions of the experiment were an electrical charge of 0. The U-tape, or tape B, which acts as our system, is measured and placed on a base tape before being stripped off quickly to create a positively charged tape through the removal of electrons. This positive charge will thus be repulsed by the introduction of tape A, the surroundings, and will result in the apparent levitation of tape B, as seen in the diagram. Tape A and tape B were measured to be 0.2 meters long with a mass of 2 times 10 to the negative 4th kilograms. The separation distance between the tape is 0.025 meters, and the magnitude of gravitational force and the magnitude of electric force are equal and opposite forces acting on the tape, as seen in the free body diagram. The two main vertical forces on the floating portion of tape B, as previously mentioned, are the gravitational force, which points downward, and the electrostatic force, which points upward, and the two forces are balanced. The measured electric charge on the floating tape was found to be 1.166 times 10 to the negative 8 coulombs. From this, the area of the atom is used to determine the number of atoms present on the tape. From this, the number of deficit electrons can also be determined, and the ratio of electrons transferred from the tapes are also determined through dividing the number of deficit electrons with the number of atoms per tape. The atoms on the tape are sufficiently separated from each other, so there are no interactions between adjacent atoms. The number of excess or deficit electrons is solely determined by the atoms on the tape surface and is not influenced by external forces. The first computational model treats each tape's charge as a single point at the center of the tapes. Q is calculated through the square root of tape 1's mass times the force of gravity times the separation distance squared all over our constant K. The model returns a diagram showing the gravitational force and the electric force present on charge B, as well as a value for the ratio of deficient electrons to the atoms present on the surface, which is found through the number of electrons by the number of atoms present, as previously mentioned. The second computational model treats each tape as a series of point charges, where the electric field is represented by the green arrows, the gravitational force is represented by the yellow arrow, and the electrical force is represented by the white arrow, all on tape B. The value Q, which was determined to be 2.582 times 10 to the negative 8 coulombs, is determined through trial and error in order to maintain the magnitude of electric force and the magnitude of gravitational force previously determined for this model. The discussion questions ask, what would happen if electrons and protons were to exchange signs? And the answer is the direction of the electric field would swap between the charges. Protons would point inward and electrons would point outward, yet the repellent and attractive forces between charges of same and opposing sides would remain the same. Next, we are asked to compare our Q value for each computational model and our experimentally calculated value And we find that the point charge model and the line model are drastically different. The differences between the two computational electric charges can be attributed to the fact that there are more charges present at further distances from one another and will thus result in a larger Q for the line model in order to equalize the magnitudes. The line computational model is more likely to be closer to the real value as it is a better representation of the distributed charge along the tape. Some sources of error come from a mishandling of the charged tapes, which could lead to a potential discharging of them. Also, the assumption that both tapes possess the same amount of charge is not realistic. Some comparisons between the experiments are: the experiment conducted in real life involved a distributed charge across the tapes, whereas the computational models assumed a point charge or an equal charge distribution for simplification. The main result of this experiment are that like charges repel and opposite charges attract, and objects can lose or gain electrons, resulting in a new net charge.